All right, kids, how are you today? Hope you're doing well. We are going to start lesson 8.6. This should be the last lesson of our liquids and solids and intermolecular forces unit. And then we'll do solutions next. But this will be lesson 8.6. I'm going to talk about phase diagrams for a little bit, then I'm going to talk a little bit about water. So let me minimize or get rid of this picture of me and we can jump right into the notes. Again, just like in class, you ought to be following along and kind of taking notes on in your blanks and filling this out, and we'll go from there. Okay, so we're going to talk about phase diagrams here. Phase diagrams, and here's one on the screen right now, I think. And there we go, there's one on the screen. This is the phase diagram for water. You'll see that there are several different regions of space. And I've got my laser pointer now. So this region that's located on the left side of this phase diagram is typically the solid phase. It says it right here in bold blue. I apologize for the drawing. They've got pictures of water molecules in there in the solid and liquid and gaseous phase, so you can get an idea. We got the solid on the left. We've got the liquid kind of up in this central upper portion, and then this portion down in here represents the gas phase. And most phase diagrams you can pretty quickly and easily figure out where the solid, liquid, and gas phases are. Sometimes they're labeled, sometimes they won't be. I do want to point out too, on the y-axis we've got pressure being listed, and on the x-axis we've got temperature being shown. So really what a phase diagram does is it describes the different states and state changes that occur at various temperatures and pressure conditions. There are several major features of a phase diagram. First of all, let's talk about the regions, which I just represented and showed you. The regions represent states, the solid, the liquid, and the gas states or phase, and I'll use the words gas and phase interchangeably. And then the lines represent state changes, so that this line right here, moving up and down, represents the fusion curve, or the phase change between solids and liquids, what we would call melting or freezing, depending upon which direction we're moving in. The sublimation curve is kind of located below that. That's just simply the phase change in going from a solid to a gas. And then this curve right here would represent the vaporization curve, and that'd be going from a liquid to a gas. All right, so again we have our phase diagram. Major features of a phase diagram: the liquid and gas line is the vapor pressure curve, which I just showed you a moment ago. On this line, both excuse me, both phases exist simultaneously, so they are in equilibrium of each other. So right along here, along this curve, this vaporization curve, the liquid and the gas, if they occupy any specific pressure and temperature that puts it right on this curve, that tells us that we have a liquid and a gas kind of in equilibrium with each other. The critical point, up here in the upper right-hand portion, the critical point is the farthest point on the vapor pressure curve. It kind of shows that temperature above which a substance cannot exist in the liquid phase. So really what I think happens is we take a line here and we just shoot it straight up. And if I can draw a perfectly straight line here, it would look something like that. We have a line that goes straight up, and then all of a sudden that liquid just doesn't matter what the temperature is. If it was at a temperature beyond that, it would be a gas, and pressure would just be increasing straight up and down that line. The triple point, located right here where the three lines kind of come together, is the temperature pressure condition in which all three states exist simultaneously. Notice we're looking at water here, and maybe I ought to make a comment about water. This line right here, this straight line, dotted line right here, is at 760 torr, which is equivalent to 760 millimeters of mercury, which is equivalent to 1 atmosphere. We would refer to that as standard pressure. So that line right there represents kind of normal pressure conditions. You'll notice then that this point where the fusion curve hits the 760 torr is, we read straight down, is 0 degrees Celsius. That is the normal freezing point or the normal melting point of water, 0 degrees Celsius. And if we keep going across to the vaporization curve, this point right here, where pressure is 760 torr or 1 atmosphere, we see that that is the boiling point or the normal boiling point of water. Remember, we define normal boiling point to be the temperature at which a liquid goes to a gas at standard pressure. So, and for water, we know that to be 100 degrees Celsius. So water's triple point is found to be at a temperature slightly above 0 degrees Celsius, but fairly well below 760 torr. So we don't see water hitting its triple point under normal conditions. It's not something we would see. We would have to manufacture those conditions to get ice, water, and steam kind of existing all together at the same point or at the same time. Okay, for most substances, the freezing point increases as pressure increases. All right, so here's a slightly less confusing look at the phase diagram for water. It doesn't have all the background pictures in it. So again, we've got the solid phase of water, the liquid phase of water, then a gas phase of water. Here's the triple point. And what we've done is we've kind of blown it up to a little bit so we can kind of see a little bit more detail. 1 atmosphere is up here, that's normal pressure. Down here, very low pressure, 0.06 atmospheres, and you can kind of see some standard temperatures and pressures along here. So if we had normal pressure conditions for H2O in kind of a cold condition, so this temperature where I've got the laser pointer set at, this temperature is slightly above negative 25 degrees Celsius. Maybe it's actually negative 25 degrees Celsius. It's almost like that problem that we worked in the previous lesson. If we're going to convert negative 25 degrees Celsius ice into 125 degrees Celsius water, what would we have to do? Well, we just heat it up, and at some point, 0 degrees Celsius, it would go from solid to liquid. We keep heating, we keep heating. Here we are at room temperature. We keep heating, we keep heating, we keep heating. Then we get to the boiling point, the normal boiling point of water. It turns into a gas. We keep heating up to 125 degrees Celsius or so, and we've gone through all 3 phases. So if we follow that top horizontal line from about negative 25 degrees Celsius all the way to 125 degrees Celsius, we get that kind of change, and we see that water will go from the solid phase to the liquid phase and then to the gas phase. If we were right here at room temperature and we decrease the pressure on water, we would find that that water would be would slowly and sufficiently and at some point reach this equilibrium vaporization curve. And if it dropped below this pressure, which isn't marked, but if it dropped below that pressure, which is probably just around 1 or 2 atmospheres, we can turn liquid water into gaseous water without raising its temperature. And that's kind of what I did for you in that day when I in class when I hooked the vacuum pump up to water, and we lowered the pressure above the water, and we were able to boil water at room temperature. So that's what we were seeing there. All right, let's take another picture, another two phase diagrams. On the left, we had the phase diagram for iodine, and we can see that it still has those 3 areas. It has the solid area, the liquid area, which kind of exists in the middle of that Y. See how these lines kind of make a Y shape? Well, the liquid phase of iodine kind of exists in the middle of that. And then down at the bottom, or to the right of the Y, is the gas phase. Notice the triple point for iodine is here. We can find on the pressure axis, we can find here's 1 atmosphere of pressure. So under normal conditions of pressure, we can take iodine, which would be at room temperature, would be a solid, and we can heat it up into its liquid phase and then ultimately into its gaseous phase as we went through the various points there. Carbon dioxide has a little bit different phase diagram look to it. Here's 1 atmosphere normal standard pressure for carbon dioxide, but notice that that is below the triple point, so that when we take carbon dioxide at fairly cold temperatures but 1 atmosphere of pressure, which is pretty easy to replicate in a classroom or under normal conditions, and we heat up that solid carbon dioxide that it goes straight into the gaseous phase and it sublimes. And that's what dry ice does. Solid carbon dioxide is known as dry ice. At standard pressure, if we heat that up, it will simply turn into vapor or carbon dioxide vapor. Carbon dioxide's triple point is located at 5.1 atmospheres and about negative 56 degrees Celsius. So its phase diagram looks a little bit like this, and we can kind of follow our way through that. So let's look at this first question. What state transitions occur when a sample of carbon dioxide at negative 60 degrees Celsius and 10 atmospheres is warmed to 30 degrees Celsius and 10 atmospheres? So this just requires us to look at the phase diagram. So I'm going to try to toggle back and forth here. In your notes, you might have to turn back and forth between pages 18 and 19. But if we're going to look at if we're going to look at carbon dioxide and see what kind of phase change it goes through, we want to find negative 60 degrees Celsius, which is going to be somewhere in here. And we're going to find 10 atmospheres of pressure. Somewhere there's 5, some are called 10, maybe somewhere right here. And if we go from negative 60 degrees Celsius and we stay at 10 atmospheres and we warm to 30 degrees Celsius, well, 30 degrees Celsius is right over here, almost to this horizontal or this vertical dotted line. We're going to see that carbon dioxide will go through all 3 phases. It will go from a solid to a liquid to a gas. If we look at the second question, we want to describe what state transitions occur in carbon dioxide if you begin with a sample of carbon dioxide at negative 60 degrees Celsius and only 0.5 atmospheres, and we warm it to 30 degrees Celsius while keeping pressure at 0.5 atmospheres. Well, we've got to flip back to our graph, which we can do here, I think. Yep, there we go. So we're at 0.5 atmospheres, so somewhere down in this range, and we're going to go from negative 60. So we're going to start here. So we're definitely in the gas phase, and we're going to warm it to 30 degrees Celsius. Hey, we stay in the gas phase the whole time, so there actually is no state transition. It's completely in the gas phase the whole time, dealing with carbon dioxide there. All right, so that kind of finishes phase diagrams. I'm going to put up a worksheet for you to do under the assignments, and you'll see that, and it will be that actually will be pen and paper worksheet that you'll get to do. I want to talk for just a minute about the extraordinary properties of water, just because water is quite interesting. What we find is that water is a liquid at room temperature, which is odd because most molecular substances with a similar molar mass to water, pretty small, are gases at room temperature. We think about ammonia and we think about methane. Both of those have ammonia's molar mass is about 17, methane's molar mass is about 16, so pretty close to water's 18 grams per mole molar mass. We find that those two are definitely gases at room temperature, but water is a liquid at room temperature. This certainly must be due to the hydrogen bonding that happens between water molecules, that really incredibly strong hydrogen bond that tends to form there. Water is an excellent solvent, dissolving many ionic and polar molecules. We're going to talk about this in the next unit, in Unit 9. It has a large dipole moment, and even some smaller non-polar molecules will dissolve a little bit in water. Both oxygen and carbon dioxide will dissolve in water. We know oxygen dissolves in water because that's what fish breathe when they swim around underwater. And we know carbon dioxide dissolves in water because our favorite soft drinks are based with carbonated water, which is carbon dioxide dissolved in water. Water has a very high specific heat content for a molecular substance. We talked about that a few units ago when we were talking about that. And finally, water expands when it freezes at a pressure of 1 atmosphere. If you have ever put a bottle of Coke in your freezer and come back a couple of days later, or hopefully not a bottle, but if it was a bottle, definitely plastic, that bottle of water will certainly have kind of expanded out, maybe even exploded. If it was a glass bottle, it will definitely explode and create a huge mess. If it's a can of Coke, it will usually bubble out the bottom, but water expands to about 9% of its volume, so 9% bigger in volume, mostly due to those hydrogen bonds that kind of lock into place when they go from their liquid state into their gaseous state.